Give me one. Pick one.
Endothermic.
Is?
Oof. Could it be like when you touch ice, maybe?
Well, no. First, tell me what does endothermic mean?
Oh, when a substance takes in heat.
Absorbs energy. So absorbing energy is endothermic. And while he's talking, go to table I. That's not out yet. Go to table I. And if you touch ice, explain.
The ice takes the heat from your hand.
Good. Ice is taking energy from your hand, so that is endothermic. Good. What's exothermic mean, Matt Payne?
It releases energy.
Good. Release energy. Give me an example.
Fire.
Give me a better example. Because fire is tricky. Yes, fire is exothermic.
It's not really a reaction.
I mean, it is, but if I light these papers on fire, so the fire is already created from the match. Or let's say I had a match or a lighter. But really, where does fire come from? You probably don't know how to answer that. It's created because there's a spark or a certain amount of energy that ignites fuel, some sort of fuel source. And a fuel source is something that's made of chemicals or compounds and elements. So it's burning that. So when you light paper on fire, really it's the paper that is burning. The flame isn't burning itself. The flame is burning the paper. So the paper is actually releasing the energy, which in turn is the fire. So it's a little bit harder to understand with fire. But yes, fire is exothermic. Give me another example. Maybe something that is on this front table here that we've talked about. Like this thing here.
The heat pack.
Yeah, hot pack. If you feel a hot pack, it gives you energy. That is exothermic, okay? So I walked around, you touched the flask. It got cold, really cold. Is that an endothermic or exothermic process? It feels cold to us. Endo, because it's taking our heat. The substance is taking, so remember, we're thinking of it in terms of not us, but the substance, right? This is giving off heat. The flask I just held, or you just held, is taking heat. So endo and exothermic in terms of the substance, okay? And then how we react to that or how we feel to that, right? So, good. Those are good examples. Go to table I. Now, table I, at the bottom, very bottom of the chart. So write in our notes, table I. Bottom of the table there. Morgan Thomas, read what it says. A little asterisk, I think.
The H values are based on molar quantities represented in the equations. A minus sign indicates an exothermic reaction.
Good. Minus sign indicates exothermic reaction. So, actually, I wrote that in our notes, but didn't we put endo over here and exo over there?
Yeah.
Yeah, I wanted to add this to it, sorry. So, endo, exo. So we wrote the definition, then we said it feels cold, feels hot. Underneath that, okay, endothermic, I want you to put a positive delta H or positive Q. That doesn't make a whole lot of sense right now, it will down the road. Exo is a negative delta H or negative delta Q, or negative delta H or negative Q. Let me get rid of that dash there. So on table I, if you look at those reactions, go to the top right of table I. You see how it is labeled delta H or triangle H? Triangle means delta. Delta means the difference, so final minus initial. Delta means difference, difference in energy. H stands for heat, it also stands for energy. The unit is kJ, which is kilojoules. Joules are units of energy. We'll talk more down the road about that. But anyways, if you look at the very first reaction, that's a combustion reaction. That's where you burn CH4. Burning, that's actually methane, natural gas. So when you burn natural gas, it releases releases 890.4, is that the number? 890.4 kilojoules. So why are we talking about this? How is this useful? On a Regents, if the question says, given the following reaction, and it gives you the first reaction on table I, so the question will give that to you. Is this exothermic or endothermic? You would go to table I, you would look up the reaction, you would go to the right, find the number. The number is the amount of heat. It's either gaining or releasing. If you see a negative number, it's releasing it, it's exothermic. If you keep going down that chart, the first positive number is like, I don't know, what is it, 140 something? No?
182.
182? 182.6. So that would be the first reaction that absorbs energy. Those reactions feel cold to us. Okay, it would absorb energy. So positive delta H, what does that mean? Positive here, put in parentheses here, heat. Positive heat or negative heat. Positive heat or negative heat. So I'm just introducing table I. We're going to learn a little bit about this kinetic theory thing, then gases. There's some stuff you need to learn about gases. And then we're going to come back to heat a little bit. So I'm introducing it because it's conservation of energy. That's when we learn that. So you don't have to know everything about table I right now. Just know it's there and know how to read that number. Negative means it's getting rid of the heat, and then positive means it's gaining. The Q we will talk about down the road. I'll show you right now why I'm bringing that up, but right now we're going to kind of leave it alone. Go to the back of the reference table, very back. Very back of the reference table. Everybody go to the very back. Mike Flower, back of the reference table. Find the heat formulas. There's 3 of them. Q equals MC delta T. Q equals MHF. Q equals MHV. You don't need to memorize them. They're all right there. What does Q stand for? Heat. Says it right there. Okay? So anytime from now until June, the end of the year, if you get a positive Q, a positive number for that Q, it means energy is being absorbed. If you get a negative Q, energy is being released. So again, I'm introducing the concept of heat and the sign. Positive means gain. Negative means lose. If you have a bank account, if you ever have one in the future, and you have a negative on your bank account, that means you in fact overdrew. You took too much money out. Or if you have, let's say, $100 in your checking and you write a $200 check, you're going to have minus $100. That's bad. That means you lost money. Okay? You're losing. The concept there, the analogy is negative means losing, getting rid of. Okay? If you have a positive balance, that's good. You have money. You gained it. You put money in, you have it. That's positive. So positive means gain, negative, lose. Okay? So that's kind of the gist of it. And those 2 words, endo and ex, are real important to remember. Okay? Real important. And they both apply to physical or chemical changes. That one in the fume one I just did with you, the cold one, that's a chemical process. This is physical. This is physical. I can reverse this. This is just crystallization. This white stuff is sodium acetate, and it dissolves in water. There's a little tiny bit of water in here. You can't really tell. There's a little bit. If I heat this up, it will dissolve. I'm actually going to go do that right now. I'm going to put it in the beaker in the back here, and hopefully by the time the bell rings, I can show you that it all dissolved again. All right. Just got to put it in boiling water for about 10 minutes. I'll probably forget about it and have to show you on Monday, but that's likely. All right, so that's enough of that. Okay, now, temperature conversion. Temperature conversion. All right. All right. There's 2 scales. There's the Celsius and there's Kelvin. Fahrenheit doesn't exist in here. Don't worry about Fahrenheit. Celsius and Kelvin. Now Kelvin is unique. Over here I want you to make a little mini graph in your notes. Big enough so you can write on it and read it. But Kelvin's unique. So if we have the temperature here in Kelvin, which is just capital K, and we plot it versus the kinetic energy. We talked about that yesterday. I'm going to give you a little bit more notes on that today. But the kinetic energy of particles, in this room, there are particles bouncing around, moving around. So kinetic energy is energy due to motion. And the temperature, so right now, this little egg thing here keeps temperature. And it says we'll just round it. It's 22 degrees Celsius. That can be converted to Kelvin. The Kelvin temperature scale measures the average kinetic energy, and that's what temperature does. We learned that yesterday. Measures the average kinetic energy. We're going to write that in a second. But the thing is with these two is it has this kind of relationship. As the temperature goes up on the Kelvin scale, the kinetic energy also goes up. What is that called? What type of relationship is that? What is it? Direct relationship. Good. Direct relationship. It's proportional. As one goes up, the other goes up. Kelvin's the only scale that does this. There's another reason for that, and I'm going to explain that a little bit later. But Kelvin is an important scale that we need to understand and know how to convert. Kinetic energy we'll define again in a minute, but here's our two scales, Celsius and Kelvin. Let's define temperature. Colin, I think, will remember this for the rest of his life. What is it, Colin?
Let me see. I got it in here.
The measure of?
The average kinetic energy of a substance.
Measure of the average kinetic energy of a substance. And what is kinetic energy? Kinetic energy is energy due to motion of particles. Some particles move fast, some particles move slow. Average would be the average of those two particles. Let's use speed, for example. If one particle is going, I'll just give you a number with a unit. Let's say 100 joules. So one particle, this particle is flying through the air at 100 joules. And then we have another particle flying through the air going 200. What would the average be between those two? 150. Temperature would say, okay, the average is 150, and that translates to a certain temperature. So that's what it means. Over near the heater, particles are moving real fast. Over in the corner on the floor, particles are moving real slow. Interesting is all particles always collide and hit each other. That's part of the kinetic theory we're going to talk about in a couple minutes. But temperature measures the average of that. So some move quick, some move slow. Temperature takes the average. All right? Okay. Let's learn how to convert this. Go on the back of the reference tables again. Hopefully you didn't put them away. Hannah, can you read me the conversion or the formula for converting? Just find the word temperature.
K equals Celsius plus 273.
There it is. Write that down, please. K equals degrees Celsius plus 273. All right. Now, if we have Celsius and we have Kelvin, I want you to write that kind of next to each other there. I'm going to leave a space. Hopefully you left a space. I left a space here on purpose. If I have H2O solid and H2O liquid at equilibrium, it's called, with these arrows, one arrow going that way, one arrow going this way. So if I have ice, solid water, and liquid water at the same time, so I have a phase change. I have solid turning to liquid. What's that called? Melting. If I have liquid to solid, Tyler? Liquid to solid.
Liquid to solid.
Very good. So if I have melting and freezing and it's water, it's happening at the same time, almost like a slushy. Nicole, what temperature on the Celsius scale does that happen? 0 degrees Celsius. Very good. 0 degrees Celsius is where we have freezing and melting of water. Water melts at 0, it freezes at 0. It depends on what you start at. If you start as ice, it will start to melt at 0. If you start as water, it'll start to freeze at 0. Both of those occur at the same time, depending on what we're doing. You're getting warmer or colder. What about, we'll go down here, H2O liquid in equilibrium with H2O gas? That's like a little cursive L, by the way, in case you're wondering what the heck I'm drawing there. That's an L. It's just I write it pretty messy. So SLLG there, solid liquid gas. So liquid water, gas, water is gas, which is water vapor. What temperature does that occur? Where we have, what's liquid to gas? It's evaporation, but if we have, well, I'll just say it even though this is not right, and you're going to learn why it's not right, but I'll say it. If we heat water up, what happens eventually? It'll boil. So liquid to gas is boiling, gas to liquid condensing. What temperature does that happen at? 100 degrees Celsius. Okay, what's 100 minus 0? 100. Very good. Olivia thought that was funny. Who can convert this to Kelvin using that? Watson can. Give me the freezing point of water in Kelvin. You don't have to look at anything. Look up here. 0 degrees Celsius converted to Kelvin. Plug the 0 in for that. 273 K. Notice how there's no degree. There's no degrees. It's just Kelvin. It's just a unit of Kelvin. There's no degrees in Kelvin. Okay, trickier one now, Trevor. This one's tough. Convert that to Kelvin. 373. That was a hard one. Good job. All you have to do is add 273 to whatever Celsius is. That's Kelvin. The equation's on the back of your reference table. You don't have to memorize it, but you will. Okay? It gets tricky when we have negative numbers for Celsius. In fact, here's a question. Can Kelvin ever be negative? No. Let's prove it. And I want to prove one more thing real quick here. What's the difference between these two? That was pretty bad. 100. This one's better. That's a little better. What's the difference here? 100. So the difference between 1 unit of Kelvin, so 273 to 274 would be 0 to 1, right? That would be 1. That would be 274. That is never going to be any different. In other words, if this goes up by 1 degree, that goes up by 1 unit. It's just the difference is a number of 273. So there's a difference between this and this as far as the conversion, but the way the scale is set up, it's still the same difference between the temperatures. So if you have 10 degrees minus 5 degrees, that's the same thing as 283 and whatever I just said, 278. So the difference is the same in each scale. So that's important to remember. Now, if I have a negative Celsius, let's say I have negative 30 degrees Celsius. What is that in Kelvin? You might think, oh, it's a negative number. You can't have negative Kelvin. So how would we do this? We plug this in here. Kelvin equals negative 30 plus 273. What does that really mean? 273 minus 30. What does that equal? 243K. You can't have negative Kelvin. That's why Kelvin is directly proportional to kinetic energy, like that graph we drew. There's no negative numbers. Negative kinetic energy doesn't make any sense. Everything, kinetic theory is everything is always moving. Everything. Wait, this marker's not moving. What are the particles doing in the marker? Vibrates. Technically, everything is moving. So Kelvin never gets below 0. Does anyone know? Write this down. What 0 Kelvin is called? Absolute 0, right. This is called absolute 0. And it's really just a theory. All motion stops. Scientists think if you get to 0 Kelvin, everything stops. Even that vibrating of solids, everything stops. And by the way, electrons are constantly moving. And the theory is if you get to absolute 0, even electrons stop moving. I guess scientists in labs have gotten like within a fraction of a degree of it, but that's the deal. 0 Kelvin, absolute 0, all motion apparently stops. That's the lowest temperature that exists. What is that in Celsius? What is this? What's 0 K in Celsius? Plug in 0 for that. Negative 273, right. So negative 273 degrees Celsius is the coldest temperature that we theorize that can exist. Because we say you can't go below 0. Right now it's 22.8 degrees Celsius in here. Imagine if it was negative 273. No, we would die way before that. Okay. way before. So these are the two temperature scales. Your homework on that one side is converting. I didn't do any with you where I give you Kelvin. That's a little harder. If I give you Kelvin, you got to subtract 273 to get Celsius. It's pretty simple math. Do that worksheet, okay? It looks like I'm going to go right to the bell. We're not done. But I'm probably not going to be able to get to anything on the other side. So I guess I'll just tell you, forget about it. Yes, after my whole speech of look it up online in the book, I didn't give you anything. So that's not fair. So you don't have to do this side. If you want to give it a shot, go ahead. But you don't have to. I'll just check this on Monday, okay? But right now, I'm going to intro the kinetic molecular theory. I'm going to show you a couple videos. We'll go to the bell. And that'll be about it. All right. So, lights, please. Oh, and I will be after school today if you need anything.
Just real quick, can we hole punch the reference table or no?
Yeah, sure, they're yours. All right. So, the kinetic molecular theory, we focus mostly on gases. And before I show you the kinetic molecular theory video, let's just real quick review how gases work. Gases bounce around constantly. They move in straight lines, so they're always moving in straight lines, and they move randomly. There's no, this particle here doesn't, have like an address or a map in its brain. It's going to do what it, do what it wants to do. It's just a gas particle. It doesn't have a brain, right? So it randomly bounces around in straight lines. But what happens is they often collide with each other. And when they collide with each other, if I was boxing somebody and I punched them in the face, what happens to their face?
It hurts.
And it could swell up, right? Black and blue, or if someone punches me in the face, right? Well, the energy from my body and my hand goes into their face when I hit it. Or if they hit me, it goes into my face. So the analogy is kind of violent, but the point is, anytime anything in the world collides, there's always a transfer of energy. If I punch somebody and there was no transfer of energy, what would happen? They wouldn't feel anything. So imagine punching something and you feel nothing, they feel nothing. That's really weird. Okay, that's impossible. So kinetic molecular theory is all about particles moving, and when they hit, they transfer energy. They give each other energy. Dang it, I didn't get to it. That's all right. We'll do it on